Good afternoon, everyone. We're going to get started here in just a moment, so sit tight and we will be right back. Okay. Hello again, everyone. Our guest today is Joe Lstiburek, whom many of you probably know or at least have heard of, but you might not know that today is Joe's birthday. So we're all going to sing happy birthday to him. No, I'm just kidding. You're all on mute. But go ahead and sing like no one's listening anyway. A large majority of construction litigation involves moisture intrusion, but it doesn't have to be that way. By properly managing moisture in the design and construction of your projects, you can help your home buyers avoid costly and exasperating problems, and at the same time, reduce your callback risk. Now, Joe Lstiburek is the founding principal of Building Science Corporation. Dr. Lstiburek's work ranges from providing expert witness testimony to overseeing research and development projects to writing for the ASHRAE Journal and BuildingScience.com. Dr. Lstiburek's commitment to advancing the building industry has had a lasting impact on building codes and practices throughout the world, particularly in the areas of air barriers, vapor barriers, and vented and unvented roof assemblies. Dr. Lstiburek is an acclaimed educator and author, and he holds a Bachelor of Applied Science in Mechanical Engineering, a Master of Engineering in Civil Engineering, and a Doctor of Philosophy in Building Science. Today's webinar is made possible by Fortifiber. Fortifiber produces a highly flexible system of products that prevent moisture intrusion, as well as the mold and rot problems that can result from leaks. The product line includes weather-resistive barriers, flashings, and sealants that, when used together, are covered by an industry-leading 15-year labor plus materials warranty. The extensive product line is based on science, and it's proven in the field. Versatile components ensure protection in every North American climate, while also providing options that support regional building practices. With its more than 75-year history, Fortifiber has become a trusted partner to builders, architects, and local building code officials. Now, during today's presentation, you can submit questions for our guest. Simply use the questions box on the right side of your screen. I'll review those questions and pose them to Joe during the Q&A time set aside after his presentation concludes. Joe, I humbly step out of your way.
Well, good afternoon, everybody. Let's get rolling here. Why am I unable to? There we go. Building is considered an environmental separator, and from our perspective, it keeps the outside out and the inside in. Every now and then, the outside gets into the thing that separates the inside from the outside, and we have to decide whether to kick it back or let it through. And sometimes the inside gets into the thing that separates the inside from the outside. We have to decide whether to kick it back or let it through. Now, the thing that we most worry about happens to be moisture, both coming from the outside in and the inside out. A material scientist looks at life a little differently than most normal people. Material scientist looks at the world in terms of damage functions, and there are three principal damage functions: water, heat, and ultraviolet light. And basically these are the three things that make things go bad for a building material or any material. And of the three, water is way more significant than heat and ultraviolet light. So if you want a durable structure, you have to address damage functions, and of the principal damage functions, water is the worst. In fact, when I was going through the ranks way back when, people that taught me said that the three biggest problems in buildings are water, water, and water. Of the various phases of water, rain is the biggest single thing to worry about. More problems occur because of rain than any other single issue in construction. And the best, the approach is you do the best you can on rain control, but you have to assume that things are going to get wet no matter how good you are. So you have to design the assembly for drying. So we try to keep the rain out. We do everything possible to keep the rain out. But no matter how good we are, some water, some moisture is going to get in. So we have to design the building to dry. So first strategy is keep stuff out. Second strategy is assume that you're not going to be successful and let things dry. The approach for building a wall or designing a wall is to have four things after we've handled the structure. We need a water control layer, an air control layer, a vapor control layer, and a thermal control layer. And they're listed in order of importance. The water control layer is way more important than the air control layer, and both are more important than the vapor control layer, and all three are more important than the thermal control layer. I've been doing this for a long time. I'm not going to tell you how old I am today, but a long time. And I've never gotten a call at 3 in the morning saying my building is leaking air. So water control is way more important than air control. Now, of these four things that are listed, the only one that we can calculate and measure with a reasonable degree of precision and accuracy is the thermal control layer. So if it's not particularly important and you can calculate it, the building code obsesses over it. You value this, I value that. The most important one is the water control layer, and pretty much the only thing that you can find is to be good and good luck. Well, we have to be good, but we can't rely on luck. I'm demonstrating here the water holdout capacity or capability of brick using an old-fashioned garden hose. Clearly, this person who's doing the test is a Canadian. He's a hoser. Okay, bad joke. The water passes through the brick in approximately 20 seconds. And so the point of this is to say that claddings leak, brick leaks, stucco leaks, everything leaks. And a good assumption is that about 1% of the water that's incident on your wall is going to pass through the cladding system, and we have to figure out a way to deal with it. Historically, one of the most successful ways of dealing with that is to put a water control layer behind the cladding system so that the 1% of the water that passes through the cladding system basically hits the water control layer and is drained downward using gravity to a way of expelling the water from the base of the wall assembly, typically with a flashing. So what we want is we want drainage to occur behind a cladding system and for drainage to occur along a water control layer. The typical brick wall historically has had a 1-inch airspace between it and the water control layer, which is in this particular case building paper. The 1-inch airspace is a historic artifact. It's not based on physics. It's based on tradition. A mason's knuckles and fingers are typically 1 inch, and that's where that, believe it or not, comes from. You don't need an inch. You can go as low as a 32nd to a 16th of an inch to get drainage if the space is continuous. So believe it or not, we're asking for an inch behind brick in order to get a continuous 32nd to 16th to a 1/4 inch gap to provide that drainage or water control. If we didn't have to worry about mortar droppings, of course, life would be easy. The issue is that the mortar droppings clog up the drainage, and sometimes we use a more sophisticated approach by basically putting a drainage mat against the water control layer so that the drainage mat provides that continuous space to provide drainage. There are many different forms of this water control layer. It evolved traditionally from the asphalt impregnated felts and type D covered papers to plastic materials, spray applied materials, fully adhered materials. They all have a place in the assembly. And we have similar materials both in residential and commercial construction. More recently, the water control layer has become integrated onto the sheathing itself, and so here we have a structural sheathing with an integral water control layer. Note that the joints have to be sealed to provide continuity of this water control layer. You can do a similar thing with an insulating sheathing. In this case, it's an extruded polystyrene. Again, the point is that the water control layer can be many forms. It can be a film, it can be sheets, it can be a combination of things. This is a fully adhered peel and stick membrane acting as the water control layer. This is also, of course, acting as a very effective air control layer and a vapor control layer, and over this would go the thermal control layer. We're also seeing spray applied water control layers that also can act as air control layers and vapor control layers. Here's a hybrid where we're treating the joints of gypsum board, which is a fire control and a sheathing, and provide some structural support, covering it with the joints with a mesh tape, and then a paint applied water control and air control layer. At the end of the day, the principles are all the same. We basically have to expel the water at the bottom of the assembly with a flashing system, and we integrate the flashing system with some kind of a water control layer. Traditionally, we did it again with building paper with the joints overlapped. This gravity deal is pretty fundamental. Gravity requires no maintenance. They haven't figured out how to tax it yet, so it's a pretty universal method of dealing with incident water. 1% of the water passes through the cladding. It's the water control layer. We rely on gravity and drainage to manage that water that penetrates and gets kicked out at the bottom of the wall. This approach of drainage is fundamental to not just the wall, but the roofs, the foundations, the site, the various components. You drain everything. You drain the material, drain the component, drain the opening, drain everything. For those of you who are American high school graduates who've never seen this before, this is a map of North America, and I point out that where it rains more, you need more rain control. You can do pretty silly things in Las Vegas and in California because it doesn't rain very much. Apparently what happens in Vegas stays in Vegas. You don't have the same luxury when you're in Seattle or in Halifax, Nova Scotia, or on a sandbar swamp in the middle of the Gulf of Mexico, like, say, the state of Florida. The emphasis on water control is directly related to the amount of rainfall that occurs annually. Once you get above 20 inches of rainfall a year, you have to be serious about drainage as well as having continuity of your water control layer. Buildings don't get wet uniformly. Most water entry occurs at where roofs meet walls at upper corners and where the building meets the ground. Where the building meets the ground, of course, the ground is wet, but also the rain hits the ground and splashes upwards. So we have, the ring around the collar basically at the base of the building with splashback, and then the upper parts of the building. Windows are their own special nightmare. When rainwater hits a window or glass, the glass, of course, doesn't absorb the water, so all of the surface area of the window is non-absorbent, so the water runs down that surface and is concentrated at the corners. We call the damage mustaching, and so basically buildings leak at the bottom of windows, the bottom of doors, where the building touches the ground, and at the edges of the building, especially the upper edges of the building, and where the walls meet the roofs. Another factor that has become very significant lately because of historical changes to building materials and the energy flow across an assembly is inward drive of moisture out of a reservoir cladding, and a classic reservoir cladding would be brick. If it rains on brick, the brick gets wet. You have to think of the brick as a moisture capacitor that is charged during a rain event. When the sun hits the moisture capacitor, it discharges both to the outside and the inside. So brick gets wet, stores water, the sun heats the water, increases its vapor pressure, and the moisture is driven both outward and inward. Well, when it's driven inward, if the assembly is too vapor open, you will drive that moisture to the inside, and it'll pass through your sheathings and your water control layers, through your cavity insulation. If you have a vapor barrier on the inside, such as polyethylene or vinyl wall coverings or epoxy paint, you're going to end up with a serious problem. And so the general rule now is do not install a vapor barrier on the inside of a building that is air conditioned. So if you have air conditioning, don't have a vapor barrier on the inside. A vapor barrier is different than a vapor retarder or a vapor throttle. Gypsum board with latex paint, not a problem. Gypsum board with alkyd or epoxy paint, you're going to have a problem. And this is exacerbated with a reservoir cladding such as brick or stucco. Excuse me. Historically, we could get away with a lot of inward drive when we had plywood, but now we have OSB, and this is a side-by-side comparison of plywood and OSB being exposed to the same temperature and humidity, and the OSB goes bad very, very, very quickly. Moisture that used to be able to be stored in plywood or passed through plywood is no longer stored and absorbed effectively in OSB, and so we have to provide a drying mechanism for the OSB that we did not have to provide for plywood. And this is especially of an issue with a highly insulated wall. So when we went from 2x4 construction with plywood to 2x6 construction with OSB, we have to change the way we handle our rainwater management. So for example, with respect to stucco, we would put stucco traditionally over 2 layers of building paper over plywood and not have an issue. When we went to 2x6s with OSB, we actually have to have a drainage gap, a space between the 2 layers of building paper, typically a 1/4 inch, to allow the OSB to dry into that space, because it can no longer distribute the moisture as effectively as plywood used to. So what we're finding is that anywhere that it rains more than 20 inches of rainfall annually, and you have stucco, and you have an OSB wall, you're going to require a 1/4 inch drainage gap to facilitate not just drainage, but to provide a space for drying. We use the term hygric redistribution, a big word that means that the OSB is able to redistribute moisture in that airspace because it's not able to redistribute the moisture within the OSB flakes themselves. Very different than plywood. This is a case where this would have not had happened had we had plywood. The wall assembly could have dried to the interior. This is an example of a little bit of water entry, but a lot of vapor driven in through a reservoir cladding called stucco. Had we had vinyl siding, not a reservoir, not a problem. So back to the fundamental principle, we actually want not just drainage but some airflow to provide a space for some drying to occur, and that airflow needs to be behind the cladding system. We didn't used to have this requirement, but again, as the materials that we construct with are more moisture sensitive, and when we have significantly less energy available to us to evaporate water, that air gap becomes critical to the durability of the assembly. What would be a good method with a brick veneer? Well, you don't want a vapor barrier on the inside. You could have gypsum sheathing plywood or OSB. You want some kind of a water-resistant barrier, WRB. 10 to 20 perms is the sweet spot. Greater than 20, you'll have too much inward drive. Less than 10, and you don't have enough drying capacity. You want a vented airspace. That means you need an air inlet at the bottom and an air outlet at the top, and you want a clear space. This is a fabulous way to do a brick veneer in the lower 48 states. When we start getting into, for example, places like Canada, we're going to require a more resistant vapor layer on the interior to reduce the amount of wetting from the interior going to the exterior, because apparently winters are longer in Canada than they are in, say, St. Louis. With a stone cladding system, it's very, very difficult to keep the mortar out of an airspace. So we provide a mechanism to create a clear airspace, typically a 3/4 inch drainage mat with a filter fabric. So you in essence take the previous assembly and get rid of the brick, but keep everything else the same, add your drainage mat with the filter fabric, and now you can add your stone. And what's nice about this is you're able to continue to provide obviously drainage, but you're also providing some airflow, and you're providing an air gap that the wall assembly can dry into from the interior into the exterior. Now both of these are in essence flow through assemblies. They can dry out and they can dry in. When we go to stucco, in essence we take exactly the same approach that we have with the stone, except the gap doesn't have to be as great. Why? Well, we don't get as much water through stucco as we do through stone, but we do need some kind of a gap. I prefer 1/4 inch to 3/8 inch, and I still want my water control, my water resistant barrier, my water control layer to be in the 10 to 20 perm range, and I don't have an issue with gypsum board as an exterior sheathing, plywood or OSB, or a great deal of insulation in the wall, with the understanding that I do not have an interior vapor barrier. I'm able to have this assembly dry both to the inside and to the outside. When the annual rainfall exceeds 20 inches of rain per year, you need that drainage mat or that drainage gap. When you're less than that, say California, 2 layers of building paper are still okay. You're in Salt Lake City, you're in Edmonton, 2 layers of building paper are just fine. You don't have the rain load that is necessary, that requires the 1/4 inch to 3 inch drainage mat behind stucco. This drainage gap is all about controlling hydrostatic pressure. If you have free drainage occurring, the water doesn't build up. That means that you don't really care about staple holes, you don't care about fasteners or cladding attachments, penetrations through the water control layer, because hydrostatic pressure is not allowed to build up. One of the ways to demonstrate this is you need to get a hockey puck, and the easiest place to get a hockey puck is, you can find them most often in the net behind a Toronto Maple Leafs goalie. But if you take a hockey puck and you put it against your water control layer, it's 1 inch thick, you've got brick. That hockey puck represents a hunk of mortar that's suspended on the wall. So if the water passes through the brick, runs down the water control layer and hits our spherical mortar, it drains to either side, and we don't particularly care. If I have 2 hockey pucks, I still have drainage. I don't care. If I have 3 configured this way, the water begins to build up. The weight of that water is what we call hydrostatic pressure, and that water exerts a tremendous force against the wall. This is, clearly a pretty bad mortar dropping brick veneer assembly, but you get the point. The secret to rainwater control is to basically not have a place for hydrostatic pressure to build up. That pressure, once you get to, for example, a half an inch of water in height, that's equivalent to a 35-mile-an-hour wind. You can basically get hurricane force loads on a wall in the absence of a hurricane. Simply, if it rains and water leaks in behind the cladding and begins to build up hydrostatic pressure, you are really stressing that wall. If you have a clear drainage space, you don't have the hydrostatic pressure, you can tolerate nail holes and staple holes through the water-resistant barrier and not have an issue. So I want to leave you with one aha thing is the secret to rainwater control is the control of hydrostatic pressure. And you don't need much of a gap to do this as long as it's continuous. Here's a plot of wind speed versus pascals, and pascals can be converted into inches by dividing by 250. So, 150 pascals is about a half an inch of water, and that's 35 miles per hour. This idea of providing a gap for hydrostatic pressure is important, especially important at corners. Here's how you do it with trim. You basically nail the trim to itself, in essence, creating this L-shaped piece, and then you hang it on the wall over a spacer strip. The spacer strip could be a very thin strip of foam. I've used sill gasket material very effectively. A sill gasket is a 1/4 inch, the thinnest layers of foam you can find, which were underlayments for the old aluminum siding, is about 3/8 of an inch, but you get the idea. This is the same works with, we have a continuous sheathing, such as extruded polystyrene. You want that small gap to occur, and it's especially critical at corners, especially behind trim. We didn't care much about this in the old days because we had the ability for these assemblies to dry, and there was energy available for the drying to occur, and we had plywood and we had board sheathing. With water-sensitive materials like engineered wood and lots of thermal resistance, this back venting and draining is very important for rain control. This is a drainage mat. Over this could be installed a paperback lath or cedar shakes or cedar shingles, and you've got a continuous airspace. These drainage mats are available in 1/4 inch to 3/8 inch, and you can go up to 3/4 of an inch. And remember, 3/4 of an inch is what I recommend when we've got a stone cladding system. But you need some kind of a filter medium to keep the drainage mat from clogging up with mortar. So in other words, you have to make sure that the drainage mat doesn't get clogged. This is with cedar shingles. In California, a classic approach is 2 layers of building paper. The outer layer is a bond break that prevents the mortar from, or the stucco itself, the rendering, from adhering to the principal water control layer, which is the one directly against the sheathing. So less than 20 inches of rainfall a year, California, OSB, 1 layer of building paper, another layer, drainage mat, or your wire lath, you're good to go. Miami, not going to work. You're going to need a 1/4 inch gap or a mesh between the 2 layers of building paper to handle the increased rain load. Here we have a WRB, a plastic film applied WRB, and we've got a a 3/8 inch drainage mat with filter fabric attached to it. Over this, you see at the bottom corner is you've got a building felt that is going to be installed with a wire lath, so we're going to end up with stucco, your filter fabric, your water control layer, and your OSB. This is actually a 2x6 assembly with an R20 wall. A little bit of physics here. If I have a cup horizontal and it rains into the cup is configured to provide drainage, and it's pretty obvious how this works. If I have it windy and the wind blows into the cup becomes pressurized. If there's no holes in the back of the cup, the wind can't get out the back of the cup. If wind can't get out the back of the cup, more wind can't enter. So I'm addressing wind-driven rain. I'm excluding wind-driven rain from entering the cup because I've pressurized the cup. Now anything that does leak in, I can still drain it to the exterior. If I put a baffle over this, but leave a part of the cup exposed at the bottom, the wind will enter at the bottom of the cup under the bottom part of the baffle and still pressurize the cup. Because the baffle is leaky, there isn't much of a pressure drop across the baffle. The pressure is taken across the back of the cup. If I have water on the surface of the baffle, I'm not going to basically suck the water across because of the pressure difference due to, basically wind. So we call this concept pressure equalization or pressure relief, where we take the pressure across the inside of the cup, not across the baffle. Now, why this is a big deal is this is the principle behind a typical glazing system. We have an inner seal and an outer seal, and we have an extrusion, which is more or less a gutter system, and we suspend or elevate the glass so that it doesn't sit in the bottom of the gutter. So we want to keep that bottom seal dry. If anything leaks, we want to drain it out the bottom and not wet the bottom seal. But that hole at the bottom that allows water to get out, should it get in, serves a very important function in that it allows air to get in to pressurize that entire chamber. And so when we pressurize the chamber, the pressure is taken across the inner seal, not the outer seal. Now the outer seal doesn't have to be very good. In fact, it's going to age because it's exposed to water, heat, and ultraviolet light. And as it ages, we don't care because there isn't a pressure drop across that seal. The pressure is taken across the inner seal. And one of the things that we've learned historically is that for this pressurization to occur, we need a ratio of 10:1 in tightness between the inner seal and the outer seal. Well, we make the outer seal 10 times leakier than the inner seal by making sure that the holes are big enough on the outside to pressurize that space. So if I have large enough holes, and that's the right word, large enough holes, you don't want the holes to be too small. You want to be able to have the outer side of this assembly 10 times leakier than the inner side. If they both start out with the same material, the outer seal is going to age faster than the inner seal because it's exposed to the outside. So the ratio always stays 10:1 or greater as it ages. So we don't care about the failure of the outer seal if the inner seal is 10 times tighter than the outer seal and we're able to pressurize that space. Believe it or not, this was figured out in the late 1950s and has been the fundamental way of doing commercial and residential windows for over a half a century. Pretty impressive. Now, what we want to do is apply exactly the same approach to the window-to-wall interface. What we want is a tight inner seal. That's where that red blob is. We want a four-sided airtight inner seal, but we want to allow air to get into that space at the bottom of the window to pressurize the space. So we want, in essence, rain shedding at the top and the sides of the window on the outside, a four-sided air seal at the bottom of the window. We want the opening to be like a gutter, so we want, in essence, a flashing system at the bottom, so that when the window-to-wall interface leaks, or when the window itself leaks, it leaks into this gutter and is drained to the exterior. So here's how it's done. We assume that some water is going to be running behind the building paper or house wrap at the between the sheathing and the building paper, and that's what's represented by these dashed lines. But we don't care about that if we allow that water to drain out. We do that by cutting a flap in the building paper or WRB at the head and sealing the flange of the window with a flashing tape or flashing membrane directly to the sheathing. When we fold that flap down, the water that's running behind the building paper hits that red horizontal flashing tape and is kicked to the exterior. So we don't direct water in at the head, we kick it to the outside. At the jambs, we fold the building paper or WRB into the opening, and then we provide a heavy bead of sealant behind the flange, and when we screw the flange in place, that acts as a gasket to prevent the water from running in at the sides of the window, and then we apply a flashing tape. So here's the sequence. It's nice to have a sloping sill. We cut the water-resistant barrier in the shape of an upside-down martini. We fold the bottom and the sides in and the top up. We put in a flashing system, so we've got side dams, we've got some slope at the back. We install our window and we provide a sealant only on three sides. We want the water to be able to drain out at the bottom. We apply the flashing tape at the jambs, flashing at the head, fold it down. We do not tape across the top of the window at the head because any water, we want the water to be able to drain out. We're still not done. We need a four-sided air seal on the inside, and that's how you do a window installation to provide drainage and pressure relief or pressure equalization at the window-to-wall interface. Pretty fundamental, but I can't tell you how many people get it wrong by not appreciating how important that four-sided air seal is on the interior. You have to be very careful with that air seal on the inside. A lot of people are using spray foam, but that spray foam can clog up the drainage gap. So whenever we use spray foam, we shove a sealant backer rod in so that the sealant backer rod acts as a backstop so that the spray foam doesn't completely go to the back of the flange. So you, speaking technically, you smoosh your sealant backer rod in to about a ½ an inch away from the flange, and then you can then spray that, you can then inject spray foam into that space, and you know that you're going to have a clear drainage space and air space between the sealant backer rod and the flange. These flashing membranes, to be effective, have to be rolled. I can't tell you what a big deal rolling these flashing tapes is. This is a slick way of doing things. There's our rainwater management, and we've got a system of furring strips to basically create that drainage gap. You don't necessarily have to install your WRB before you install your windows. You can alter the sequence and install the window first and then the WRB, but the general principles of sealing at the head are the same. And again, don't forget to roll the flashing membrane or the flashing tape to the WRB. Then your quality control, typically in commercial buildings, is we test 10% of the windows that are installed with a water leakage test. In essence, we simulate wind-driven rain by building a pressure chamber on the inside using a modified vacuum cleaner to create suction and spraying water on the outside. You don't need a very sophisticated technology to do this. You can spray this with a hose and put a blower door in your building to create the pressure difference, and so you could do a very low-tech version of a water leakage test as a very quick quality control on not just your window, but your window-to-wall interface. Why are we focusing on windows? Well, there are only two kinds of windows in the world, windows that leak and windows that will leak. So what do we know about windows? They're going to leak, especially as they get older. And so we do everything we can at the window-to-wall interface, still accept the fact that some is going to get in, and design the assembly to dry to both the inside and the outside. And there's our water test in action with the spray rack on the outside. We have other penetrations, and this is obviously a dryer event. I hate this because there's not enough of a flange on the accessory to be able to integrate the WRB to. This is just a real bad situation. But the approach to deal with it is very straightforward. You can purchase accessories that have flanges. This is a flange for a commercial installation. This is my colleague who's taking a roof jack that has a big flange on it to provide basically water management of where the refrigerant line enters the building. If it works on your roof, it's probably going to work on your wall. Some of you might recognize that as a young Professor Straub when he had hair. Of course, don't do stupid things, and one of the stupidest things is to install vinyl wall coverings on the inside that they prevent the wall assembly from in essence being able to dry to the inside, or a plastic vapor barrier. There are two sides to a wall, and it is desirable to have the assembly to be able to dry on both of those sides. You want the wall to dry inward during air conditioning, and you want the wall to dry outward during the heating season. For outward drying to occur, you're going to need an air gap between your cladding and your water control layer, especially where we have basically lots of rainfall. So let me sort of summarize all of this. Of all of the mechanisms we have to worry about, moisture and water is the most significant. The biggest wetting mechanism from a water perspective is rainwater, and where it rains more, you need more rain control. The water control layer on the outside to handle rainwater is likely going to need a drainage gap between it and your cladding system to control hydrostatic pressure, especially where it rains more than 20 inches of rain a year. When we have more than 20 inches of rain a year, and we couple it with engineered wood that doesn't have the same drying characteristics or durability characteristics as plywood and board sheathing, that drainage gap also becomes an air gap to provide drying capability. So we want the wall assemblies to be able to dry into that gap when we have high levels of insulation and moisture-sensitive materials. And then avoid the vapor barriers on the inside in places where you air condition. And with that, I'll turn you back over to Mike.
Thank you, Joe. Appreciate it much. For those of you who have questions, please don't hesitate to enter those into the questions box and send those in, and we'll be getting to those momentarily. Wanted to address the question that we get all the time, which is, are there going to be any handouts or are these slides going to be available? So I'll repeat this later on, but I'll go ahead and get to it first. The slides are going to be available tomorrow on buildingscience.com. You just need to go to the buildingscience.com website, click on recent presentations, and there'll be a PDF there. And as always, Green Builder Media records these webinars and posts those on the Green Builder Media YouTube channel. So I'll repeat that again later, but for those who are asking or wondering. All right, Joe, the first question we've got is from Tyler. He wants to know, if you've got a continuous drainage mat, such as sure cavity, and it's used behind brick or stone, does the depth of the cavity matter with respect to moisture control?
Yes and no. Terrible answer, but you don't need a 1-inch gap between the brick. You can treat the brick. If you put a 1/4 inch or 3/8 inch drainage mat over building paper and put another layer of building paper over that, you could smoosh the brick directly against that. In other words, a 1/4 inch to 3/8 inch continuous gap behind brick veneer will work just fine. The brick can drain and dry into that space. The wall assembly can do the same. Here's a warning, however. Brick masons like the 1-inch because it allows them to also straighten out the wall. It's very difficult to have a brick veneer installed over less than, say, a 1/2 inch airspace because it doesn't give the mason enough room to be able to straighten things out and line things out, believe it or not. So even though from a building physics perspective, you could pretty much get away, or not get away, it will work with a 1/4 inch to 3/8 inch gap. Experience has told me that I typically want a 1/2 inch to 3/4 of an inch in order for me to be able to give enough space for the mason to line things up. But the gap isn't as critical. That when there's that 1-inch airspace, again, it was a historic artifact. It wasn't based on measurements and physics. We could go down to a 1/4 to 3/8 of an inch, but remember, the brick installation becomes more, well, you have to become fastidious when you do it.
Gotcha. Tom had a question for stucco on a SIP wall in the Virginia, Maryland area. What type of drainage mat or system would you recommend?
Well, you have a water-resistant barrier, or WRB, of between 10 and 20 perms, and I would put a 3/8 inch drainage mat over that with a filter fabric, and then I'd put a lath and stucco, so I'd end up with stucco, a building paper or filter fabric, 3/8 inch drainage mat, my WRB between 10 and 20 perms, and my SIP panel, and I'd be in bliss. That would work just fine.
All right. Alicia wanted to know, there's some breathable barriers on the market as high as 84 perms, and they claim that the higher the perms, the better the ability of the cavity to dry. Can you speak a little bit about that?
Well, that is true if you don't have a reservoir cladding. If you've got vinyl siding, aluminum siding, you got a metal panel or a fiberglass panel, the higher the permeance of that layer, not an issue. But the moment you have a reservoir cladding like stucco or brick or wood or fiber cement, and that reservoir cladding is going to get wet, the sun will drive that moisture in, and it'll blow through that very, very high permeance layer, and it's going to get yourself into trouble. So, for example, I would never use anything greater than 20 perms over gypsum board sheathing. So let's say that I have a brick veneer and I'm installing it I'm building a platform building, an apartment building, a 3-4 story building with gypsum board sheathing on the outside. That gypsum board is very vapor open. It's around 30 perms, 30 to 40 perms. If I have a 50 perm or an 80 perm WRB, that water vapor is going to be blown through that WRB and that gypsum board into the wall cavity and cause me problems. On the other hand, if I have my gypsum board sheathing, which is 30 to 40 perms, and I've got a 10 to 20 perm vapor throttle, the inward drive isn't as great, and I'm able to dissipate that moisture in the airspace between the cladding system and the face of that vapor throttle. When I get to OSB, the OSB itself becomes the vapor throttle. But I don't want that OSB to get too wet either, so I still want a vapor throttle over my vapor throttle. So I'm going to want something between 10 and 20 perms over my OSB as well. So the OSB prevents the water from getting into the wall cavity, but I want to prevent the water from getting into the surface of the OSB from the outside as well. But I don't want to stop it completely because I want that OSB to be able to dry back to the outside. And OSB in itself isn't a perfect vapor barrier. It runs between 1 and 3 perms. I still have a little bit of drying to the outside as well. And so I want the stuff that goes from the cavity into the OSB to get out of the OSB into that airspace. So, you know, the sweet spot is between 10 and 20 perms with a reservoir cladding. Again, when I go to a metal panel or aluminum siding or vinyl siding or whatever, something that's a non-reservoir, we don't have an issue with the high perm layers.
Okay. We're going to take you south now, Joe. Fernando wants to know how you would address a core insulated concrete panel. So this is kind of like a reverse ICF. You've got an 1.5 inch concrete layer on the exterior and the interior sides and a 4-inch EPS core.
Well, that's a fabulous wall. The big issue are the joints, and so you would do 2-stage joints, basically an inner seal and an outer seal at the joint, and then you drain the space between these 2 joints. This is a common method of precast panel assemblies, and it's phenomenal. If I was to want to paint the concrete, I would use a high perm paint greater than 10 perms. Why do we know that it has to be greater than 10 perms? If it's less than 10 perms, it bubbles and blisters. So either unpainted concrete, or if you do paint the outside surface, it's got to be greater than 10 perms. And you want a 2-stage joint between the inner and outer layers, and you're good to go. The window-to-wall interface, we would typically line the opening with a fully adhered membrane. We call that raccooning, as in raccoon eyes, and then again do the 2-stage joint, a 4-sided inner seal and a 3-sided seal to the exterior. That's a proven southern technology that came to the south from the north. So there you go.
All right. Dan's question references a slide you had earlier. The stone veneer that you discussed, is that a thin stone system, or is it a laid up veneer like brick?
It doesn't matter. There's the image.
Okay.
I'll show you. We don't care. I don't care passionately or deeply. I just want that gap. So it could be a manufactured stone veneer, which I call lumpy stucco. It could be dry stack. It could be stone with mortar. All of them are going to be handled in essence the same way, a drainage mat with a filter fabric. So why am I looking to 3/4 of an inch if I've got, say, a manufactured stone veneer, which is lumpy stucco? Well, because lumpy stucco leaks more than regular stucco. That's the reason.
Okay. We got a question from David, and David's an architect. He's wanting to know if you can discuss your feelings on dew point.
I think you should go to our website and read it. Read the Building Science Insight called Confusion About Diffusion. There's absolutely no reason to do a dew point calculation. The dew point is always going to be on the backside of the sheathing, and so I'll show you an image here. Condensation is always going to occur at the insulation sheathing interface. And the reason for that is that when you have a change in phase, an enormous amount of energy is released. And fiberglass and cellulose cavity insulation doesn't have enough thermal mass to handle this change in phase energy. So for condensation to occur, you need a surface below the dew point temperature with sufficient thermal mass to handle the change in phase, and that's the backside of the sheathing. So you always are going to have the dew point location be the back of the sheathing, so the calculation is pointless.
Okay. Got a question from Douglas, and I believe Douglas is an energy consultant. He said he came across a house that had Tyvek installed under the exterior sheathing, and he had the homeowner open the drywall to inspect the wall cavity. Based on that, do you recommend any further action to identify any other damage that may be occurring to the shell of the house?
There's a lot of information missing in what you gave me. I'm assuming that the reason that the wall was opened up was because perhaps something smelled, there was a stain or whatever. If the question is opening up the wall to have a look a good idea? Absolutely. It's way more reliable than moisture meters. It's way more reliable than an infrared camera, and to me, it's the best investigation technology around. The question becomes, how many holes do you put into your building? And the answer to that is going to be, it depends on what you find. I would tend to want to look under my windows and under my doors, because those are where I probably have got my biggest risk. I'm probably going to also want to look where I have decks attached to a building or balconies, and I'm going to want to look at where roofs meet walls. And so I look at, I'll probably put a hole in the inside or the outside or both sides to look at things at the highest risk locations. But besides opening things up, I don't think you need to do anything else. I mean, that's going to tell you, from my experience, everything that, well, almost everything that you're going to want to know.
All right, we're going to ask you to play long distance consultant one more time, Joe. We're in the Denver climate. We've got cement fiberboard siding. Is one layer.
So Denver is where they have a semi-professional football team now, I think.
Oh, ouch. Is one layer, Bob's wanting to know, is one layer of Tyvek WRB okay? And there's no vent space or mat, and it's OSB sheathing?
The answer is yes. Denver gets less than 20 inches of rain a year. Tyvek or any one of those water-resistant barriers are good enough. OSB is the vapor throttle. With the fiber cement, I prefer to paint the backside of it to reduce its water control or water absorption. And it would be nice to use the commercial Tyvek. The commercial Tyvek is 20 perms. The residential one is 55. So, 10 to 20 perm WRB, OSB in Denver, fiber cement, beautiful job, beautiful. Recommend that all the time.
Okay. Lisa was going back and referencing a slide you had earlier. You had the building type wall sections. She noticed that the stucco and the stone versions did not show a low air intake or high air outlet for the drainage and drying gap. Can we assume that those are needed for all cladding types?
The answer is yes, and I hate it when I'm caught deliberately not putting information in, because it's complicated on how to put that in. And I tend to vent the wall at the top behind some kind of a band board. At the bottom, I need some kind of a trim assembly. But yes, I want a continuous gap at the top and a continuous gap at the bottom. I just didn't want to get into a lot of details on how to show it. I leave that up to all y'all to sort out.
Okay. We're here at the top of the hour, and Joe has agreed to stay on a little extra to address any further questions. So I'm putting out right now the last call for questions if you've got any. Joe, you know, I had one for you. Are you seeing any better air sealing on the inside since the energy code started making significant gains in efficiency? I'm talking like the past 5 years or so, because it took a while for the 09 to actually get into the marketplace and people start adopting it and using it. So have you seen any better air sealing in the past 5 years?
Yeah, it's been quite noticeable, quite significant. Ever since EPA's energy, thermal bypass checklist was more or less written into the code. In colder climates, we're typically seeing 3 to 4, below 3 air changes per hour at 50 pascals. And in the south, we're regularly seeing 4 to 5 air changes per hour at 50 pascals. That's a huge improvement in air leakage across the building. The reason for the difference between the north and the south is in places up north we have basements, and that's where we put mechanical systems and ductwork. In the south we don't have basements. We put our ductwork in vented attics, and that accounts for the higher air leakage. If we were to have conditioned attics, the air tightness of the buildings between the north and the south would be very similar, and they'd be in the 3 air changes per hour at 50 pascals range. That's a huge change. We were typically in the 5 to 7 range, and now we're consistently in the cold climates at the less than 3 range. That's a remarkable achievement.
Okay, thank you, sir. Brian's an architect, and he has a question. He wants to know, it's in regards to SIPs. What is your recommendation on exterior and interior? Because he's been advocating seal taping all the seams on the interior and exterior before installing drywall on the interior, TYP in drywall on the interior and WRB on the exterior.
I'm sorry, what? I didn't understand the question. I like to air seal on the exterior and the interior. I like a double seal, and I find that the gypsum board is a reasonable air control layer on the inside with all of the draft stopping, and then the exterior sheathing is a very, very good air seal on the exterior as well. So I like to see both. Help me out with the question, Mike. So
he's saying in lieu of wood or metal framing building, using SIPs instead. So if you're using SIPs, what's your recommendation on exterior and interior?
Well, it's critical that we have an air seal at the inner layer of the SIP for roofing applications. In terms of walls, it's not so critical because we're always going to see some kind of a ventilated cladding system. So I want both an inner seal and outer seal wherever possible, but the inner seal becomes critical in roofing applications because normally we put shingles on those SIP roofs, and if the inner seal isn't perfect, we're going to get moisture accumulation at that outer layer. That's been such a serious problem with SIP roofs that we recommend putting a vented over roof over the SIP panels on the roof. So we would put down our SIP panel, we put down roofing paper, we would put down 2x2s, and then we'd put another layer of plywood or OSB on the top of that, and our roofing. So we're basically putting a vented over roof over the top of the SIP panels. This is a concern. Walls, not so much.
Okay. Maria's got a question, and we're going to take you back north to Wisconsin. When you were talking about Tyvek with cement board, she's seen an increased use of LP smart siding. So do you require a drainage gap, or is OSB and Tyvek sufficient?
No, I like to see a gap. You got more than 20 inches of rainfall a year. I think you want a gap between your cladding system and your OSB. in places like Wisconsin. I just wrote a column on our website. It's the most recent posted Building Science Insight BSI. It's called Stress Release, and it deals with how to install siding and trim and to provide that gap. So the short answer is, in Wisconsin, I'd like to see a gap between my cladding systems and my WRB, and I have no problem with LP SmartSide. Both the siding and the trim work phenomenally well when you have a gap.
Okay. The last question goes to Michael. He's referencing the current IRC, and he says it asks for a vapor retarder on the inside of the wall with a Class 1 rating. Any thoughts on that?
Well, it doesn't require a Class 1 rating anywhere. I know that because I wrote that section of the code. There's no requirement for a Class 1 only. It's a Class 1 or Class 2 in all of the climate zones. There's also an exception where you can go to a Class 3 if you have sufficient thermal resistance of your continuous insulation on the outside. So Class 1 is 0.1 perms or less. Class 2 is between 0.1 and 1, and Class 3 is between 1 and 10 perms. So you can easily install a Class 2 in a place like Minnesota or Wisconsin. It does not require a Class 1 vapor retarder.
Oh, okay.
Now,
right, thanks.
there are some building officials that interpret things their own way. The practice in Minnesota is to wrap the building with plastic vapor barrier. The code, the IRC doesn't require that, but the local Minnesota code and the building officials' interpretations of it differ from the actual language of the IRC. And, by the way, the IBC.
Gotcha. All right. Well, I think we exhausted all the questions, Joe, so I want to thank you for sharing your time, your wit, and your knowledge with us today. And as I mentioned before, if you'd like a copy of his slides, tomorrow you can go to buildingscience.com, click on Recent Presentations, and you can download the PDF there. I want to thank our audience for attending and asking the wonderful questions that they did, and to Fortifiber for their generous sponsorship of this webinar. Now, we'll be right back here again 2 weeks from today, so make sure you all set your calendars, come on back 2 weeks from now, invite your friends and your family. We're going to be here Wednesday, May 17th, 2 p.m. Eastern Time. Joe's going to be with us, and he's going to be talking about building beyond net zero and enabling us to design and build homes that are net positive energy producers. So you're not going to want to miss that, so come on back. Until next time, stay dry. Take care.